Assalamualaikum and a very good day everyone. So in this video we will look at several examples for the Stokes theorem topic. For the you can see in the spectrum under Stokes theorem, week 14 of Stokes theorem. You can check. I have uploaded two videos related to Stokes theorem. Try to you must watch that video and try to understand how the how we can apply Stokes theorem. And in this video we'll look at several examples, as I said just now. So in this example we are asked to compute the path integral, okay, of f dot dr. Okay, use Stokes theorem to evaluate f dot dr, where it's stated here f, x and y and z here around a simple closed path. Here the path is given by a triangle, and because as you see here, C is a triangle with the vertices of one, so this is x, y, z, right? So 1 0 0 and then 0 1 0 for y, and then 0 0 1, this is for z. And then given by triangle whose vertices are all lie in the coordinate axis in the three-dimensional surface. So this is a triangle that lives in the plane that is not one of the coordinate planes. And let's start by we can just sketch this and then give it an orientation, and we can see that if it it actually doesn't matter where we start, but here if we want this to be positively oriented curve and have the bounded region on our left hand side as we transverse it, then it has to go like this, okay, from this z-axis, x-axis and y-axis. So what we would like to do is then evaluate this path integral, and let's do it by using Stokes theorem. So Stokes theorem says that we can instead of thinking about integrating along this path, we can call this path C, and we can enclose, we can think of any surface that is bounded by this path. So why not just think of the portion of the plane that is bounded by this path right here, and so this portion of the plane we call it as S, and that we can compute. Okay, remember that Stokes theorem says that we can compute this work done by this vector field around this path C by actually taking a double integral over the surface of the curl of this vector field dotted with ds. Okay, now if we are going to do this way, the first thing we should do is to compute this curl and the curl. So let's start with the curl. So the curl of our vector field f, okay, is remember it's a formal cross product, and the cross product is taken between what we call the del operator or the partial derivative operator, d dx, d dy, d dz, and these components of the vector field. So we have here x plus y squared, and then for the j we have y plus z squared, and then for k we have z plus x squared. And now what we need to do is actually compute this curl. So this is going to be 0 over here, and you take this partial derivative, right? So minus 2z, so, and then the first component for the first component, and then the second component is going to be 0 minus 2x, and then finally for the last component is going to be 0 minus negative 2y. And so that the curl of our vector field that we need to integrate up, and now we need to think about how we are going to represent this surface, right? So this surface is, we can think of many different ways, but this surface is a graph of a function. It goes through this point 1 0 0 1 0 1 0 and 0 0 1. Okay, so this plane right here is a portion of the plane, so any plane is just written as this ax plus by plus cz is equal to the some constant d, right? And so what we can do is we can just work this out by let d is equal to 1 and figure out what this constant have to be. And it's pretty straightforward. If x and y are both 0, then z has to be 1 right here, and then it's turned out to be true for all of this. So just by little inspection here and the nice nature of this surface in general, the equation here is actually x plus y plus z has to be equal to 1. Alright, and you can check that there's this plane, but it's gonna be right. So when x is equal to 1, everything else will become 0. Okay, everything satisfied this in the right plane. Okay, well, if you want to use the idea of parametric surface here, then what we have to do is solve for this z. Okay, so z is equal to 1 minus x minus 1, and that is then acting on it's working on some domain, and the domain is going to end up being this little portion of this portion of the triangle. Okay, down here on the plane of xy, and its function is going to take these points and map them up to the surface up here. So right, how is going to parameterize this surface here? And this domain D in this down here is the domain that is bounded. So D has, okay, now let's sketch D separately. Okay, let's just draw it. So the domain D is the one that is bounded by this curve, right? And then it's bounded like this. So this domain D here is bounded between this line right here, if you're gonna write this xy coordinates. So let's do this as a type 1 region. Then y would equal to 1 minus x, because again we have 1 and 1 here, right? Y is equal to 1 minus x. So here, how's everything work as a type, as y varies from 0 to 1 minus x, and then x varies from 0 over to 1, right? At this point, our surface is parameterized by our xy on this domain, and it's equal to the x comma y comma 1 minus x minus y. Okay, this is our parameterization function r. Okay, and the reason we use this is because, remember, here it's easy for you to get lost in what you are trying to solve here. The reason that we want to use this, because we are going to compute this integral. Okay, so we would need to compute a surface integral, and remember that the surface integral vector field are given by if you have the parameter domain, that is this double integral over s of, in this case, is the curl of f dotted with ds, and it's going to be computed as the double integral over the parameter domain of the curl of f evaluated along r. So I'm going to write it like this, dotted with the normal vector field dA. So this is what we are going to compute right here. So we need to compute the normal vector field. Okay, so let's compute that for this vector field, nu is equal to the cross product of the partial derivative of our parameterization. So r sub x is just the vector of 1, 0 and minus 1, and r sub y is the vector 0, 1 and negative 1. So this together we get that our new vector field nu, and this Greek letter nu, this vector field is 1. It's gonna be 1, 1, 1. Okay, so there's our new here, so our curl of f, let's dot them and then we can integrate them up over this domain. All right, so curl of f dot new is equal to -2. Okay, then z comma x comma y dot 2 dotted with 1 comma 1 comma 1. 1 is a constant vector field, which by the way for a plane makes it perfect sense. So this is -2 times the sum of z plus x plus y. But then remember that z is for our parameterization, right? So we have to go back up here, and x and y remain the same, but z get replaced by this formula. Z is 1 minus x minus y, and look at what happened to the term we have to integrate here. So this becomes -2 times 1 minus x minus y plus x plus y. So we can cancel this x and y. What we will get is just -2. So we will integrate this -2. So our f dot dr, this is the integral for the closed surface. Okay, so the double integral over this triangular region D of -2 dA. Okay, well, that's just -2 times the area of this region D actually, and we don't need to use calculus to compute this area. There's a lot of calculation that we need, but then we just take the area of this. This is just 1 times 1 then divided by 2, so it is just 1 over 2, right, times the 2, then here then we have -2 times 1 over 2, then we will get -1 as the value of our path integral around this triangle. So it's just -1.